I'm going to introduce you here to one of my favourite things in the course, roots of unity. Analysing these things gets really deep and dips into some university level stuff, and questions can get really juicy as well. Let's start. What do we mean, roots of unity? Unity refers to the number one. We're finding roots of the number one. These ones we can do easily already. We could have done it at GCSE. The roots of z to the 1 equals 1 gives us z is 1. Z squared equals 1 gives us z equals 1 or negative 1. Let's put those in the little diagrams already. So we've got the first one being there, and the second roots of unity being 1 and negative 1, there and there. What about the cube roots of unity, the third roots of unity? At GCSE, without complex numbers, we would say that the only solution to this equation was the number 1. That's the only real solution. But now we're working in complex numbers, we know it's a cubic, it's going to have 3 solutions. Let's work those out in the same way as the same method in my previous video. So we say if z cubed is 1, that is the same as e to the 0i, which is the same as e to the 2 pi I, which is the same as e to the 4 pi I. I'm going to use a range of arguments here that just includes positive arguments. I'm going to go all the way around that way rather than using negative arguments. Then we find the solutions by taking a third of all the arguments. So z is e to the 0i again, e to the 2 pi I over 3, and, oh, that's not an equals, that's a comma now, and e to the 4 pi I over 3. We can write those in x plus iy form, in Cartesian form, like so. That one's just the number 1. And if you use a calculator to work these ones out, I just know them on the top of my head. We would get negative a half plus half root 3 I, and negative a half minus half root 3 I. Where are those located? They are, well, we've got the number 1, and then 2/3 pi around, that is over here, and 4/3 pi around is here. And they make that lovely equilateral triangle, all with a modulus of 1. Note how I didn't do the thing with the modulus here, because all of the moduli are just 1. So any root of that will be the same. This is much more easily visualized on GeoGebra here. So what we had, the second roots of 1 were just 1 and negative 1. And the third roots of 1 are there and there. Conjugates of each other. That's what makes sense. They cropped up as conjugates of each other. Okay, what about the fourth roots of 1? Let's carry on going. If we have z to the 4 is 1, what are the roots going to be? Now, this method here of finding equivalent complex numbers and then finding the fractions of them, with roots of unity, because this is so easy and the patterns in what comes out so simple, we can just state them. So, if z to the 4 is 1, I know that my first solution is always going to be 1, so I'm just going to write 1. The next solution is going to be e to the 2 pi I, coming from that one, but then divided by 4, e to the 4 pi I over 4, and e to the 6 pi I over 4. I'm going to simplify these fractions on the next line. So e to the 2 pi over 4, that's just half pi. This one's just pi. And this one's just 3/2 of pi. And if we want to write those in Cartesian, these ones are very easy. Half pi, that's I. That one is -1. And that one is -I. These are the 4th roots of unity here. And it makes sense that they've cropped up where we found them. There, and there. In that square. Again, everything with a modulus of 1, because our original complex number, 1, has a modulus of 1. Here we go. There they are. There, and there. That one was quite neat there because it aligns with the axes. The next one, the 5th roots of unity, they're not aligned with the axes. Those are quite messy. And in that case, when writing down the 5th roots of unity, we're just going to use this method again by just writing them down, following the pattern. So we'll end up with 1, as usual, 2 pi I over 5, 4 pi I over 5. Have I missed one? No. 6 pi I over 5 and 8 pi I over 5. We've got 5 of them. The next one would be 10 pi I over 5, which would just be the same as that. These are the 5th roots of unity. And none of these fractions cancel here. 5's a prime number. There's no nicer way of writing them. We can just write them like that. Those there are the 5th roots of unity. I do want to go on to the next one. This is the last one that I'm going to do. The 6th roots of unity. Because something nice is going to happen here. So end up with 1 again. Maybe you can pause here and get ahead. What are the 6th roots of unity going to be? Pause it now, maybe. I'm just going to go ahead. I'm going to do it. I'm excited. We've got e to the 2 pi I over 6, 4 pi I over 6. Those are the 6th roots of unity. But a lot of these cancel down. So we've got e to the 3rd pi I, e to the 2/3 pi I, e to the pi I, e to the 4/3, and e to the 5/3 pi I. You might already be noticing where these have cropped up before. We have all of these are the 6th roots of unity. What do we have within that? Well, a couple of these have cropped up before. The 3rd roots of unity were 1 e to the 2/3 pi I, e to the 4/3 pi I, and they're cropping up here. 2/3 pi I, 4/3 pi I. We've also got within here the 2nd roots of unity. We've got 1 and -1, being that one and that one. These other ones, where do they slot in? Well, thinking about that hexagon that we'd get, we have within it, let's see if I can skip back and forth between these. The 3rd roots of unity are there, and there. So just focusing on these complex ones. And they are there and there. And then these other ones that crop up are like the negative version of those. We've got this yellow one is the negative of this pink one, and this purple one is the negative of this green one. It's like flipped around. But importantly, that the 6 roots of unity include both the second roots of unity and the third roots of unity. Why is that? If we carried on with this and did z to the 7 equals 1 and listed them all out, which previous ones will that include? Similarly for z to the 8 equals 1, and if we list out all 8th roots of unity, which previous ones will that include? Maybe you could predict it and then do it. Think about both the algebra and the geometry. If we did the 8th roots of unity and thought about the geometry of it, that would look like an octagon. Which previous roots would that include? That's a question for you to dwell on there and figure out yourself. One last thing that I want to mention, a good technique here, with any of these, if we take the first one that we wrote down that wasn't the number 1, so in z to the 4, that would be that one. In z cubed, it would be that one. In z to the 5, it would be that one. And z to the 6, it would be that one. Notice the theme between all of those. If we have z to the k equals 1, then our first root that isn't the number 1 is, I'm going to call it w e to the 2 pi I over k, that's what all of those were. Then all of the other roots can be based on this one. The next root is just w squared. The next root after that is w cubed, all the way up until you have k lots of roots altogether. So we can generate all the roots of unity from just that first one there. That's a useful technique of sometimes writing these down, and sometimes exam questions refer to that as well. I'm going to leave you with sort of animation of that. If you focus on that yellow one there, and I press play here, we'll see powers of that yellow one go round, and it should hit all of the others. This can be fairly quick, so watch out. So that yellow one there, squared it hits there, w cubed it hits there, w to the power 4, w to the power 5, and w to the power 6, it gets all the way back. So all of the other roots can be based on just that first one. I said I was going to leave you with that. I'm going to leave you with the question that I asked you before. Let me remind you of that question. If we were to go up from here and do the next one, z to the 7, z to the 8, which of the previous roots would be included in those? Can you think of a general rule that would carry on all the way up? Have fun with that.